In taking a look at problem number 3, the one thing we need to realize first is we'll analyze this in a second. You have harmonics here. They want to know what fraction of the total length, this being L, what fraction of the total length is how many waves are present within that length, and then the actual wavelength itself. Before that, it's important that you understand the two equations we use, the calculating the frequency of different harmonics, and that is that the nth harmonic will equal n times the velocity of that wave divided by 2L for an open-open or a closed-closed. And for an open-closed, which is, again, open-closed, a little bit odd, they're different, that's over 4L. I just want to very quickly make sure you understand that in terms of an open-open or closed-closed, closed ends provide nodes and open ends provide antinodes. So take a look here. If n is 1, well, we're starting here. And as you can see here, the first wave that will fit in here that has a node on each end would be something that looks like this. It's no different than when you have a string, but what you have here is you have 1/2 of a wave. That's the first wave that you can fit within this pipe that has a node on one end and a node on the other. You need to realize that everything is based off of this fundamental frequency. So if I want n equals 2, I take whatever I had for n1, and I need to double that. So instead of half a wave, my next one has to have one full wave because it's twice my fundamental frequency. So in order to have that, I have a wave that looks like this. And as you can see, when I doubled what I had first, when I went from 1/2 to 1, I still had a node and a node. So that means that n equals 1 works and n equals 2 works. Well, if I want to add a third harmonic, what we have here is I had a half to begin with, so I need to add 3 of those, 3 halves. So I need to have half, half, and another half. And if you see this, hopefully it's starting to make a little bit of sense. I have a node on one end, I have a node on the other, so that means n equals 3 will work as well. So this is one of the things we mentioned previously, but when you're dealing with an open-open or a closed-closed, n can be any number, 1, 2, 3, so on and so forth. It can be any because each increment, so if I have a half that works, if I double that and have 2 halves that works, if I have 3 halves that works, and when I say that works, I mean within the boundary conditions of this pipe. So that's why n can be 1, 2, 3, first harmonic, second harmonic, third harmonic for an open-open or closed-closed. It's a little bit easier to deal with. We have something that's slightly different when we're dealing with an open-closed pipe. So again, closed ends produce nodes, open ends produce antinodes. So the first wave that I could fit in here would be something that has a node on one end and an antinode on the other. Now this tends to be confusing for some people, but if you take a look, just draw a wave, that's one full wave, and if you look, we're actually going from a node here all the way up to the top of an antinode, and we stop. So we just have to take a look and say, well, what fraction of this entire wave is this section here? And hopefully you can see that from a node to an antinode, that's going to be 1/4 of the wavelength. So what we have here is we have 1/4 of this wave. That's our fundamental frequency when n equals 1. So what we need to do now is, if we want to know if there's technically a second harmonic, we need to double what our first one was. Well, if we had 1/4 and we double that, well, we start on a node, and if we double that, we have 1/4, and we have a second quarter. That gives us half a wave. And what we would wind up with is something that looks like this. But hopefully you realize that this cannot happen. We can't just have a node in the middle of empty space. So n equals 2 does not work at all, because in order to have that work, you'd have to have a node on both ends. That's not possible. You'll never have a node on an open end. You'll only have an antinode. So n equals 2 or 2/4 will not work because we can't have a node on an open space. But if we take out 3, well, we have 1/4, 2/4, 3/4. And if we take a look at that, that gives us a node on one end, an antinode on the other. That's fine, because 3/4, again, everything's based off of this fundamental, this quarter wave. So 3/4 will work in terms of giving us a node and an antinode. So what we have over here is we have 3/4 of a wave. And hopefully you start to see that when n equals 1, we have 1/4. When n equals 3, we have 3/4. Hopefully you can realize what happens with 5 and 7 and the 9th harmonic. You have 5/4, 7/4, and 9/4 respectively. But again, just to double check 4. Well, 4 would be 4 times larger than 1. So instead of 1/4, we would have 4/4. That's 1/4, 2/4, 3/4, 4/4. And if we look at this standing wave, Again, we have a node on this end and a node on the other end. This is not possible. Again, these two are not possible, so therefore n cannot equal 4, and this process will repeat itself so on and so forth. So if we take a look, n can only be 1, 3, if you continue this 5, 7, 9, must be odd. All right, and that's an important concept to realize, must be odd. And again, one is closed, one is open. That's kind of odd. They're a little bit different. Maybe that helps you, but n must be odd in this case. So moving forward, if we understand that, we should be able to take a look at problem number 3. Hopefully this makes more sense now. We have open, closed on all of these, so there is no second, fourth, or sixth harmonic. There's actually no even harmonics whatsoever. Again, first harmonic, if we want to draw that in, should just look like this. First wave that we could possibly fit in there. Well, this is L. L fits in 1/4 of a wave, and if 1/4 of a wave is L, then the total wave must be 4L. Okay, 1/4 of it is L, so the total must be 4L. That's like saying 1/4 of a door is 1/4 of a door is 2 feet, so the total door must be 8 feet. You're given 1/4 is L, so the whole wave must be 4L. Now you know you can't have 2 because 2 would give you a node and a node. So what you need to have here is 3/4 because everything's based off this quarter wave. 1/4, 2/4, 3/4. All right, and if you take a look at standing wave, that looks like that. And as we just discussed, you have 3/4 of a wave. Hopefully you realize 4L is the reciprocal, or 4 is the reciprocal of 1/4. So what's the reciprocal of 3/4? Well, this would have to be 4/3 L, which again would be 1 1/3. So 1 1/3 total length of L. Here, hopefully you see we need 5/4 because everything's based off the quarter, 1/4, 2/4, 3/4, 4/4, 5/4, and if we complete this, what we wind up with is we have 5/4. What we have, right, the 5/4 is 1 1/4. Well, we have 1 1/4, and the reciprocal, the total wavelength would be 4/5 of L. Well, we have 1, 2, 3, 4, 5/4. 1, 2, 3, 4 of them make up one wave, so 4/5 of L. Hopefully you see by now 7. We're going to need 7/4 because it's all based off the fundamental frequency. So 1, 2, 3, 4, 5, 6, 7. And if we continue this, node, antinode, node, antinode throughout, this will be 7/4, and this will be 4/7 L. So taking a look at problem number 3, hopefully you understand what's going on with this. If we take a look at problem 4, well, again, we just have to realize here that overall these equations are Fn equals NV over either 2L or Fn equals NV over 4L, depending what you're talking about. The important thing to realize is if you're not changing the length and you're not changing the medium, the speed will remain constant and so will the length. So the only thing that actually changes here is going to be your N. If you find your fundamental frequency, well, F3 is just 3 times that frequency. F5 is 5 times that frequency. F7 is 7 times, and so on and so forth. So if we take a look here at problem 4, we're being given that the first harmonic, which would be F1, is equal to 786 hertz. And what they're asking for is, what is the third harmonic? You don't even have to use all these crazy equations. If you realize that the length and the velocity hasn't changed, the only thing that will change is n, well, F3 is going to be 3 times larger than F1. So keeping that in mind, 3 times 786 will give you, oh, I apologize. What they give you is the fundamental frequency of 262 hertz. I apologize, 262. That will give you 786 hertz. So if you have your fundamental, well, the third fundamental frequency, the third harmonic frequency is going to be 3 times that. 3 times 262 will give you 786. If you want to look at part B, well, they're giving you the, let's see here, the fifth harmonic. So you're given the fifth harmonic is 1700 hertz, and they want to know what is the fundamental. Well, you should be able to realize that since n is the only thing that changes, F5 is 5 times larger than F1. Therefore, if F5 is 5 times larger, I should be able to divide it by 5 and get F1, and that will give me 340 hertz. So it works in reverse as well. F1 to F3 multiply by 3. F5 to F1 divide by 5. Taking a look at C here, this one is a little bit tricky. You're given F3, and you're told that that's 984 hertz. I find the easiest way to do this, take F3 and divide it by 3, which will give you F1. So if we take that, and let me just double check. So if we take 984 divided by 3, we get that the fundamental frequency is 328 hertz. And we know that F5 is going to be 5 times larger than that, which is going to give me 1,640 hertz. There's multiple ways to do this mathematically. I find that that tends to be the easiest. Last but not least, we're given D. You're given that the fundamental frequency is 210 hertz. And you want to know the next highest frequency for an air column whose fundamental frequency is that. We can assume they don't give us open, open, or open, closed. I'm going to assume open, open, which means that the next highest would be F2, which is going to be 2 times F1, which should give you 420 hertz. If you had chosen a open-closed pipe instead, obviously the next one you can't have 2 would be 3, so it would be 3 times F1, which would give you 630. That's if you assumed that it was an open-closed pipe. I had a really traumatic experience with the number 5 when I was a child, so we're going to go ahead with problem 6 because I like to pretend that 5 doesn't even exist. I don't want to go back to that place. You can't make me. So here we're looking at 6A. 6A, you are given something that looks like this, I believe. Not the best one I've ever drawn, but you're given something that looks like this. 6B, let's see, 3 antinodes, 1, 2, 3, and down. 6C, I'll get to in a second. So you're given 6A, and they tell you that the length of this here, 35 centimeters. Hopefully you realize immediately we hate centimeters. B is 56 centimeters. Again, we don't like centimeters. So here's what we have to look at. Well, we need to know, they're asking for the wavelength. So they're asking, what is the wavelength? We have the length. All we have to do is figure out what fraction one wave makes up. This is closed open, so it's easier to look at quarter waves because they're all multiples of that fundamental frequency. We have 1, 2, 3, 4, 5. So we have 5, and our wave takes up 1, 2, 3, 4. So 4/5. So that means that 4/5 of L must equal our wavelength. Well, we know our length is 35 centimeters, so 4/5 of 0.35, and that should give us 0.28 meters. It's all about looking at what fraction of this length one wave takes up. Take a look here. Well, we have 56 centimeters as our L. Well, 1, 2, 3, 4, 5, 6, 7. So there's 7 quarters. And 1, 2, 3, 4. So 4 of them, I apologize. So what we have here is 7 sections, 1, 2, 3, 4, 5, 6, 7, and our one wave takes up 4. So 4/7 of the total length is going to be one wave. 1, 2, 3, 4, 5, 6, 7, and our total length is 0.56 in meters. So 4/7 times 0.56 should give you 0.32 meters. For C, they don't draw you a picture, but it's a little bit easier to see if we draw that out. So for C, let's draw out our first harmonic. Well, our first harmonic has 1/4 of a wave. So the entire length, which they give us, is 32 centimeters. Well, we know that 0.32 meters equals 1/4 of a wave. Okay, so if we want to figure out what a full wave is, well, we just multiply by the reciprocal. And we should realize that here that the wavelength is 4 times that length, which is 1.28 meters. Hopefully this is nothing profound. If we'd like to take a look at problem D, again, drawing a picture will help us. 5th harmonic, so we need 5 quarters because it's open-closed. 1, 2, 3, 4, 5. If we complete that, we are given that this is 1.2 meters. It's in meters, we're happy. So what we need to do here is take a look. We have 1, 2, 3, 4, 5. 5 sections, 4 quarters. So 4/5 of that total length will be one wave. So the wavelength is going to be 4/5 of 1.2, which is going to be 0.96 meters. For problem 7, you're given a lot of information, but at the core of it, they just want to know what the fundamental frequency is, the first harmonic. Well, we know that F1 is going to be n is 1. We know we're going to have our velocity, which is given to us as 340. We're going to divide that by, we're told it's an open closed, so that's going to be 4 times our length, which we're told is 17.2 centimeters. And for those that don't see what I'm doing here, I'm just taking this equation because 4, it's an open closed system, and I'm just plugging in first harmonic, velocity, and our length, and 4 is our constant. If we plug all of this in, you should find that your fundamental frequency equals 1,976.14 hertz. It's just a matter of plugging the variables we have into the equation that we have. If we take a look at problem 8, what we're going to take a look at here is we have a closed end organ pipe. So that means we have one end is open and one end is closed. What we're given here is we are given the third harmonic frequency, which is 1,100 hertz. We're also given the fifth as 1,833 hertz. This is fairly simple. They want us to find the fundamental frequency. We have two options. We know that F1 is going to be 1/3 of F3, so we can just take 1,100 and divide it by 3, and if we do that, we get 366.67 hertz. Well, we also can take the fifth, which we know is going to be 5 times larger than F1. Another way of saying that is F1 is going to be 1/5 of F5. So we can take our 1833 divided by 5, and what do you know? We get 366.67 hertz. You can do it either way. It's just showing you again that each of these harmonic series, each next step is going to be just a multiple of the fundamental frequency. And last but not least, we have problem 9 here. So we're given problem 9, and we're told that the harmonic frequency of one of these bottles is 349.2 hertz. We're told that the velocity is 345 meters per second. And we want to know what is the length of this pipe. Well, hopefully you realize that if it is a, what do we have here? Open closed system, we have F equals NV over 4L. We're given our fundamentals, so we know 349.2 hertz is going to equal, our N is just 1. Our velocity is 345, 4 times L. We just have to do a little bit of algebra, multiply both sides by 4L. That cancels. We're then going to divide both sides by 349.2. What we wind up getting here, when I do all of this, I understand it's a little bit crazy all at once. We get 4L is actually equal to 345 divided by 349.2. I will then divide both sides by 4, and what you're given is L equals 0.25 meters.